Alright, so this is part 2 of 1.4 and 1.5 notes screencast. So this is where we left off. So the next item, okay, and now keep in mind what we're doing here is leading up to electron configurations. Okay, so the next part is we have the Pauli exclusion principle, and kind of the key thing there is in bold. An orbital can only hold 2 electrons. Okay, so that's the maximum capacity. Each individual orbital. Okay, so if we're talking about individual orbitals, it doesn't matter if it's an S, P, D, or F orbital, it can hold 2 electrons. Now it also says here opposite spin. Now that's not really a big deal, but we'll see this when we do the orbital diagrams at the end. The spin is represented by the direction of the arrow. So if you have an up arrow and a down arrow, that represents or shows that those electrons they're spinning in the opposite direction. One clockwise, one counterclockwise. So you always want to have one of each in each particular orbital. So you don't want to have 2 that are pointing in the same direction. But anyway, an orbital can only hold 2 electrons. Okay, next you have the Aufbau principle and the periodic table. So valence electrons. So valence electrons are pretty much what chemistry is all about. Every chemical reaction is how the valence electrons are reacting. What are they being lost or gained or shared? How is the atom moving the valence electrons around to try to become stable? So really chemistry is all about valence electrons. Valence electrons are defined as electrons in the outermost principal energy level of an atom. So they're the ones involved in bonding and reactions. And elements in the same group have the same valence electron configuration. And we want to determine the number of valence electrons from the periodic table. So you'll probably want to label this on your periodic table. Alright, so here we go. So the alkali metals, including hydrogen, which isn't an alkali metal, but it's in this group, they all have 1 valence electron. Alkaline earth metals, they have 2 valence electrons. Let's skip over to here. This group has 3, the carbon group has 4, nitrogen group has 5, oxygen group has 6, the halogens have 7, and then the noble gases have 8, except for helium, which only has 2. Okay. The transition metals in here, they do some different things with their electrons, so don't worry about the number of valence electrons there. Same thing with the inner transition metals that are down here, the lanthanide and actinide series. Technically, you could say that both of these big groups have 2 s electrons, but don't worry about valence electrons here so much. Okay. Right. Next, we have the Aufbau principle. That's how electrons enter orbitals of lowest energy first. So they fill the orbitals closest to the nucleus first, until they've hit their capacity, and then they keep moving farther and farther away to higher energy levels. Then you have Hund's rule, where electrons enter orbitals of equal energy with parallel spins first, then they fill. What that means is that electrons don't pair up until they have to. Got to keep in mind they have the same charge, and like charged things don't like to be next to each other. So we'll see this more when we draw out orbital diagrams, but here's kind of a preview. Here's a 2p group of orbitals. So these are equal energy orbitals. So the way this would fill up, you'd put 1 electron in this orbital, you'd put your second electron in that orbital. So these orbitals, these electrons, they don't pair up because they can spread out into other orbitals. This is how you would draw it the wrong way. You're pairing them up and before you have to. So electrons don't pair up until they have to.
Staff, if you are wondering why the link to
next,
the Learning Lab is not working,
we have
your email. I have provided a new one. Sorry. Thanks. Bye.
Okay, next we have orbitals, sublevels, energy levels, and the periodic table. So again, this is building us up towards electron configuration. So we can use the periodic table to determine the order in which orbitals are filled with electrons. So keep in mind, individual orbitals can hold 2 electrons. Okay? Then you have sublevels, which are groups of orbitals. And there's 4 different types. There's S, P, D, and F sublevels. And these sublevels correspond to the blocks on the periodic table. So up here in this table, you can see the different sublevels. And this is how many orbitals are in each sublevel. And then this is the also the number of electrons. So an S sublevel is just an individual orbital, so it can hold 2 electrons. But a P sublevel is a group of 3 p orbitals that can hold 6 electrons. A D has 5 orbitals, can hold 10 electrons. F has 7 orbitals, can hold 14 electrons. I said that corresponds to the blocks on the periodic table. So these are your blocks. So the S block is these first 2 columns with helium included. Helium, you could kind of put it right there. The P block is this section right here. The D block is the transition metals right here. And the F block is your intertransition metals right there. Okay, so you probably want to label your periodic table accordingly. So you probably want to, it would be good if you would label 1s, 2s, 3s, label all these things on your periodic table. You can always get another periodic table if you need one, but for electron configurations, this will help quite a bit. Okay, next you have energy levels. So we had orbitals, we started with that can hold, an individual orbital can hold 2 electrons. Sublevels are groups of orbitals. Now the next thing is energy levels are groups of sublevels. So energy level corresponds to the period on the periodic table. So going back to this, the number in front of the letter, that's your energy level. So you can think of the first energy level is just going to be this 1s sublevel right there. So it's only an individual orbital. But now if you go to the second energy level, now you have 2s and 2p. Those 2 sublevels make up the second energy level. Now if you talk about the third energy level, now you look at everything that starts with 3. So it's 3s, 3p, and 3d. So the capacity of the third energy level now is 2 plus 6 plus 10. So now that's 18 electrons. When you go to the fourth energy level, now you have 4s, 4p, 4d, but now we also put in 4f. So now we have 2 electrons plus 6 plus 10 plus 14. Now that gets us up to 32 electrons for the capacity of the fourth energy level. So these are the 4 energy levels, and if you just know those first 4, that's all you need. Okay? So these are the sublevels that are in those energy levels. This is the total number of orbitals, and this is the total capacity of the electrons. Okay, so now we're up to electron configurations. Okay, so with the electron configurations, you may have learned like a longer version of those to begin with, but we're just going to cut right to the shortcut method. It's also called the noble gas notation. So it's easier and it's quicker, so that's the method that we're going to use. So with that, we start with a noble gas, and the reason we can start with a noble gas is because they have full energy levels. So it's a good reference point, it's a good starting point. So, and that's why noble gases are stable. That's why they don't react, because they don't have to. All the other atoms will try to react to become like a noble gas. So noble gases have full energy levels of electrons, so that's going to be our starting point. So then we want to use your periodic table to finish the electron configuration. So we have 2 examples here, chlorine and calcium. So chlorine, go back to the periodic table here. Chlorine is right here, on your periodic table. Okay, it's in this 3p sublevel. So you want to start with the noble gas behind the element. So basically it's the noble gas one row up. So it's this noble gas right here. It'd be Ne with neon. So you put neon in brackets, and that just means that all the orbitals up to where neon is are full. So then you start in the next row. Okay? So our first sublevel is 3s, and we can place 2 electrons in there. So you put a superscript 2. I'll show you what it looks like in a second. And then you go to the 3p sublevel, and chlorine's the 5th element in, so you'd go 3p with a superscript 5. So what that looks like is that. So neon in brackets, 3s2, 3p5. Calcium, show you the answer for that one too. For calcium, go back to the periodic table. Here's calcium right here. So we go back to argon, and we would put that in brackets, and then you start in the next row. So this sublevel is 4s. It's in the 4th row, it's in the s block, and it's the second one in. So it's just 4s2. Okay. Now here's another 4 of them. So I would suggest just trying that out. You can pause the video, try those out, and then I'll show you the answer in a second. I'll talk through those. Okay, there's the answers. Yeah, for iron, you go back to argon, and then you always start with the S block. Okay, so we're in the 4th row, so it's going to be 4s2, but then you go 3d6. So the energy level for D is always 1 less than S. So for Te, start with Kr in brackets, and then it's in the fifth period, so you go 5s2, 4d10, 5p4. For sulfur, you start with neon in brackets, and that's in the 3rd period, so go 3s2, 3p4. And then Ra, which is all the way down in the bottom left corner, you use Rn as your noble gas, and then it's just 7s2. Okay, and then you also want to be able to do electron configurations of ions. So I have a couple of examples here, a few examples. So the sulfide ion, the calcium ion, and the iron positive 2 ion. So with ions, if you have a negative ion, that means you've added that many electrons. If it's positive, you've lost that many electrons. So sulfur with a negative 2, if you go to their periodic table, here's sulfur. It has 16 electrons to begin with. But now if we make it a negative 2 ion, it becomes like argon. The term for that is called isoelectronic. The sulfur negative 2 ion is isoelectronic with argon. So it's going to have the same configuration as argon. So you would go back to neon, put that in brackets. You can't just put argon in brackets and be done. You always got to go back. So you put neon in brackets, then 3s2, 3p6. And that one's done. And that's what the answers are for those 3. So sulfide is isoelectronic with argon. Calcium, because it loses 2 electrons, is also isoelectronic with argon, so they end up have the same electron configuration. But now iron positive 2 is a little bit different, and this goes for all of the transition metals. When transition metals turn into ions, it's the s electrons that are lost. Like if you have neutral iron, the electron configuration would be Ar 4s2 3d6. The 2 electrons that are lost in the process of forming this ion are the 4s2 electrons. So you wouldn't want to write 4s2 3d4. That's not what really happens. So please remember that when you're doing transition metal ions, you lose the s electrons first.